So moving into our last special sense is equilibrium. Remember, equilibrium is also found in the ear, not associated with the cochlea, but associated with the vestibule and those semicircular canals. So we have this whole vestibular apparatus then that is going to have vestibular receptors for what's called static equilibrium, and then semicircular canals in those three different directions for what's called dynamic equilibrium. The dynamic equilibrium part is also sometimes called rotational equilibrium, and we'll find out why that is coming up. Okay, so what we find is when we're talking about that vestibule, we have these maculae, and these are the ones that are monitoring the static equilibrium. And so with these ones, what we find is these particular receptors will respond to what's called linear. Remember, the other ones, the semicircular canals, were more dynamic or rotational. These ones are more linear. So moving forward and backward, moving up and down, straight up and down like in an elevator, or just the position of your head relative to gravity, right? So gravity is always kind of pushing down on them, but if I have my head slightly to the side, I don't need the visual stimulus to know that I'm not exactly upright, right? So when you wake up on the bathroom floor after having bad tacos or whatever happened on Friday night, and before you open your eyes and see the side of the toilet, you can actually know that your body position has changed because of these maculae inside of the vestibule. Good to know, right? All right, so what we find is we're looking in here. So here's our vestibule in here, and the utricle and the saccule have these maculae that are in there. So what we find is that these are hair cells again. We had hair cells in the cochlea for sound waves. Now we're having it for equilibrium. And these hair cells have stereocilia as well, but they also have this one particular one that's called the kinocilium. And so when we look at it, the kinocilium ends up being a particularly, we see one here, and one here, and one here. See that long one, right? So it's associated with those other stereocilia, but they're all sitting in kind of a gel-like matrix. And on top of that are a bunch of ear stones. Now that was always interesting to me as a marine biologist, because I always heard about stones in the ear of otoliths that are in the ears of fish. And so it was one way that you could age a fish is you could take out the ear otolith stone and you could look at the rings on it like the rings on a tree. Now, that's not entirely accurate, but that gives you the idea of growth. So we have otoliths as well, but we have many ear stones. So what's the idea with these ear stones? So the ear stones, like we said, sit on top of the stereocilia with the long kinocilium, and they move. And so when you are vertical, like you see in the top there, gravity's weighing on them, and it gives a little bit of a signal there. But as you start moving forward or moving backward, right, these ear stones are going to kind of pile up on one side or the other. And as they do that, as they move in one way or the other, it's going to cause a bending of those hair cells, either towards or away from that one kinocilium, like we said. And when we look at the neural output then, we can say that's going to change the frequency of the action potentials. Because remember, action potentials, they look the same every time. So there's no change in amplitude, but there can be a change in frequency. And so that is something that the brain can interpret. So moving forward, moving backward is going to change the frequency of these action potentials coming in, and the brain can then interpret that in terms of our movement. So again, this can be movement itself. With the up and down, you're going to get more gravitational pull on it, right? And then when we're moving forward and backward, you're going to, again, kind of leave those behind or be leading them, etc. So even something like this, right, all those little ear stones are going to be ding, 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 ending up on one side and then affecting those stereocilia and kinocilium underneath. Okay, so utricle and the saccule are going to be associated with, like we said, static equilibrium. And so also known as linear equilibrium, and so moving in straight lines or even kind of the position of your head relative to gravity. So now when we get to the semicircular canals, when we look at those, what we find is at the base of each one, like here and here and here, what we have is this interesting looking structure here. And that is called the crista ampullaris. And the crista ampullaris has hair cells in it as well. So you can see them sticking up through this, again, gelatinous matrix like this. No otoliths anymore, but what we have is a bunch of fluid in these semicircular canals that move around. And so much like the endolymph, like we saw going through the cochlear duct, this endolymph is moving around not by sound waves, but by changes in terms of turning your head, turning your body, as you might be rotating, like on a roller coaster or something like that, right? And so what happens is, and here is a scanning electron micrograph of that ampullary cupula there. So that whole structure that we see right here is a cupula, right? So the whole crista ampullaris includes the rest of the supporting cells down here, as well as the hair cells, and then we can see the nerve fibers coming from it. So in any case, what happens is, right, we remember that those semicircular canals were organized in the X and Y and Z directions. So it doesn't matter what way you're turning your head, right? Fluid within one of those canals is going to be sloshing around. And this crista ampullaris is flexible. And so as the fluid kind of washes by, it's going to cause that ampullary cupula to bend. And again, when these mechanoreceptors bend, opens up channels, causes depolarization of the cell in most cases, and then what we find is generation of a gradient action potential. So it's kind of like if you were walking around and you had a drink with you, like a cup of coffee or something like that, and you're walking, you make a sharp turn, right? The fluid in your cup of coffee is going to continue along that path that you were moving, and it's going to slosh all over the place. And that's what's going to happen in the endolymph in these semicircular canals. So depending on which one is sloshing, that's going to tell the brain kind of which way we're rotating, etc. And if you do something like that, right, this fluid takes a while to kind of calm down. So you get that feeling right afterwards of that kind of movement still as these cupulas are kind of settling down and the fluid or endolymph is settling down as well. So, like skaters and things like that, right? They're going to get a lot of sloshing as they're spinning around. And when they stop, it doesn't immediately stop. And sometimes you'll even, right, think about what happens when you stop spinning and your eyes sometimes do this kind of saccadic tracking. And so what happens is, right, you're still getting the sensation from the semicircular canals that you're spinning, and the eyes are trying to catch up and go, okay, well, what are we looking at next as we're spinning around, spinning around, spinning around? So that's a reflex that they'll automatically then slow down and stop doing once this endolymph in the semicircular canals slows down and the cupulas stop being stimulated. Okay. So when we get information about the position of the body, its space, etc., it comes from the vestibular receptors, like we saw, comes from the visual receptors as well, right? If you were laying again on that nice cool bathroom floor or something like that, you're not going to get much from your visual receptors. But once you open them, right, that the information will combine with what you're getting from your vestibular receptors, as well as, like we saw before, you know, those tendon receptors and different types of somatic receptors that are telling us what's going on with the joints and what's going on with the muscles, giving us an idea of our overall body position. And so that goes to the cerebellum as well as the brainstem, and that allows us to kind of be aware of, but then also to control our position in space. And what happens then if your vestibular signal is different from your visual signal? Oh, so they think that that's where the problem arises in motion sickness, whether on a boat or in the car or whatever. So what happens is, when you're in a car or you're on the boat, right, you and that vehicle are moving at the same rate. And so for your eyes, looking at the inside of the car or looking at the inside of the boat, you're moving, but the boat's moving as well. So to your eyes, everything is static, not moving. But that doesn't fool your vestibular receptors, which are getting this, right, linear motion as well as rotational motion. So due to this conflict, they think that that's what causes motion sickness. Now, why certain people are more sensitive to it than others, that's a good question, right? People that can't read in the car, again, because you're focusing on that and you're getting this idea by moving, so that conflict, that happens as well. So what do they tell you to do, right? If you're not feeling well, stop looking at the book, look at the horizon. If you're looking at the horizon, now you're getting the idea that you're moving, and so now there's a match between what the eyes are receiving and what the vestibular apparatus is receiving. Now, one other short topic associated with the ear has to do with deafness, right? So we've talked about all types of structures that are associated with receiving those sound waves, and if something happens to those receptive structures, then you're going to get what's called conduction deafness. So this could be a Q-tip stuck in your ear, right? It could be perforated eardrum or something like that. It's not bouncing as much, as well as if you have an ear infection, right? That pharyngotympanic tube, you get a throat infection, it migrates right up to your ear, and you might not be able to hear very well. But then there's also sensorineural deafness, and that comes from instead, right, the hair cells as they wear away, or if there's the area of the brain, like in the temporal lobe, that's not able to receive those signals, then in that case, the receptors are kind of doing their job, or the tympanic membrane, etc., but we're not actually getting the signal into the nervous system. So, depends on where the damage is or where the problem is as to what type of deafness and what type of solution there may be, right? If it's something like the sensorineural deafness, then it doesn't matter about putting some type of a hearing aid on there to amplify the sound, right? So what we find is, in that case, you just have a loss that's inner ear and neural instead. So, in any case, hopefully you won't get too much of that now or later. Now, like we said, some of these different receptor structures do tend to decline through time. We talked about that happening with your eyes, right? So myopia, hyperopia, things like that. The chemical senses tend to dull through time as well, even though we know that those sensory neurons recycle pretty quickly in terms of the olfactory receptors and the gustatory receptors. Still, they tend to dull through time as well. So odor and taste detection tend to be poor at about 65 and older. So that's why like spicy foods and things like that, well, they can add a little bit more. It's not quite as maybe as noxious to those that are younger. But vision and hearing, we all know, kind of decline as well. So something to look forward to. But in the meantime, use all those special senses in your learning, and then hopefully this will stick with you so that you can learn for the test, and then also know how your body works as well as those of your potential patients.